In this video, we will grow sodium chloride NaCl crystals using a simple evaporation method. This technique involves dissolving salt in water, allowing the water to evaporate slowly, and letting the NaCl ions to come together to form crystal. Our goal is to observe the resulting crystals with the naked eye and identify their distinctive cubic geometry. Throughout the process, I have made several attempts at growing NaCl crystals. Some of them turn out cloudy or irregular, while others form sharp icicle-like structures, and eventually achieve this clear and transparent crystal. I will show you all these attempts to highlight the challenges and learning points along the way. First, let's take a look at the NaCl crystal. At the atomic level, NaCl forms what is known as a face-centered cubic lattice, or FCC lattice. This structure is made up of alternating sodium cations and chlorine anions, arranged in a highly ordered three-dimensional grid. Each ion in the lattice is surrounded by 6 oppositely charged ions, creating a strong ionic bond. These bonds not only hold the structure together, but also give NaCl its stability and unique properties. In an FCC unit cell, the ions are positioned at each corner and at the center of each face of the cube. When these unit cells are repeated over a large scale, they created the overall cubic symmetry of the crystal. This explains why the macroscopic crystals of NaCl, which we observe with the naked eye, naturally form a cubic shape. To grow NaCl crystals, we will need hot water, filter funnel, coffee filter, containers, and some salt. In my experiment, I have used some table salt, which is the iodized sodium chloride salt, and some Himalayan rock salt. For my first trial, I decided to use the Himalayan rock salt. Here is what I did. First, I fill a glass container about 1/4 full with the Himalayan salt. Then, I pour hot water into the container and stir it thoroughly until the solution becomes saturated. Once the solution was saturated, I filtered it using a coffee filter to remove any impurities. Then, I added a small amount of salt back into the solution to trigger nucleation. After that, I let the saturation sit undisturbed for a day. After a day, I noticed that there is no crystal form. Instead, I only found salt powder settled at the bottom of the container, along with the salt that I had added. From this trial, I concluded that the solution was only saturated. For crystals to form, the solution needs to be supersaturated. So with this learning, I moved on to trial 2. For my second trial, I decided to use iodized salt. This time, I wanted to ensure the solution was supersaturated. Here is what I did. I dissolved the salt in water while heating it until it started to boil. As the water boiled, I noticed that the amount of undissolved salt at the bottom of the pot increases. At this point, I quickly filtered the solution into a glass container. As I shine a light on the solution, I observed a stunning phenomenon. The solution sparkled, almost like snowflakes falling. These sparkles are the points where crystallization occurs. Unlike in the first trial, crystals start forming immediately. Why does this happen? When we boiled the NaCl crystal, it became supersaturated because the hot water could dissolve more salt than room temperature water. As the solution cooled, tiny NaCl crystals began to form at the bottom through a process called nucleation. These microscopic crystals reflect and scatter light when illuminated, creating the sparkling effect. However, I noticed that the crystals formed were not cubic but elongated, resembling icicles. This is because when I pour the hot supersaturated solution into a cooler container, the sudden drop in temperature caused the NaCl crystal to crystallize too quickly. Rapid crystallization doesn't allow the ions to arrange themselves into a stable and symmetrical cubic form, leading to elongated or irregular shapes like icicles. For my third trial, I used the same iodized salt and heating process to achieve a supersaturated solution. However, instead of waiting for the water to start evaporating, I poured the solution into a glass container just before evaporation began. This time, I observed small square crystals forming within 10 minutes. These crystals floated on the surface of the solution initially before sinking to the bottom. Unlike the icicle-shaped crystal from trial 2, these were distinctly cubic, though they appear opaque. Why were they opaque? The opacity could be due to the contamination from impurities or dust in the solution. It might also be a result of the crystals forming too quickly, preventing them from achieving a perfectly clear and ordered structure. For my fourth trial, I decided to use a very slow evaporation method to grow larger and clearer crystals. I started with the same crystal from trial 3. Since most of the crystals had already formed after a day, I filtered the solution again to ensure it was saturated. Next, I poured about a centimeter thick layer of the solution into a flat plastic container lid and covering it to prevent contamination. After a day, I observed tiny transparent cubic crystals with dimensions around 1 mm x 1 mm. Over the course of a week, these crystals grew to approximately 2 mm x 2 mm x 1 mm in size. To achieve even larger crystals, the solution would be need to left undisturbed for a month or more. By then, you could produce crystals as large as 1 cm x 1 cm using this very slow evaporation method. From all these trials, I learned that the best way to grow clear and transparent NaCl crystals is to boil the solution while dissolving the salt to achieve supersaturation, allow the solution to crystallize for a day before using the saturated solution to grow seed crystals. Lastly, use a slow evaporation method to let the crystals grow larger and maintain their clarity. Thanks for watching. Have fun growing your own crystal.